Alright, let's move into arc length. And the idea behind arc length, as you probably would have guessed, is it finds the length of your curve. If you were to pick up your curve, straighten it out like a string, and lay it on the x-axis to measure it. So arc length finds the length of the arc. Pretty appropriate name. The way arc length works, we're going to generate the arc length formula using the same thought process that we used back when we used Riemann sums to estimate the area under a curve. So we're going to break this up into subdivisions. So I have the subdivisions. I'm going to break it up into several little subdivisions. And in order to estimate the length of the curve, so I want to know the length of this curve from A to B, I'm actually going to connect all of those subdivisions with linear segments. And so I'm approximating this curve by using linear segments, and then using the good old-fashioned distance formula, I can actually find the length of each one of those segments. So this is going to look an awful lot like the distance formula. Your distance formula, if you don't remember, is a change in y squared plus your change in x. Whoops, that's not an x. Squared. Or you could, instead of using y2 minus y1, you could say it's the square root of delta y squared plus delta x squared. You're changing y and changing x that way. So finding those and adding those together gives you the approximate length. So I'm going to say the length of the curve. We will just define the length of the curve to be L. And so the length of the curve is actually going to be approximated by taking the sum of all of these distance formulas. Whoops. Change in y squared plus change in x squared. Well, just like with Riemann sums, with area, you have your approximation, and if you want it to be a more accurate approximation, then you simply take more subdivisions. So we'll break this up and we just use more linear segments. And if you wanted this thing to be exact, then you would take this sum and see what happens as the number of subdivisions approaches infinity, and that's how we're going to get our arc length formula. So my actual arc length, if I take an infinite number of subdivisions, this thing, the sigma, turns into the squiggle s, stands for sum, and my function in here is going to be the function inside my arc length formula. Only when you take an infinite number of subdivisions, your delta y becomes infinitely small, and we represent that as a dy squared. Your delta x also becomes infinitely small, and so that would become a dx squared. And then we would measure this from A to B in order to get to your arc length. Now, one thing you may notice is in this arc length formula, we are missing what we typically have on the outside, which is a dx or a dy, to tell you what your primary variable is. So the way we fix that is we do a little bit of algebra here. On the inside here, I'm going to multiply everything by 1 over dx squared. So if I distribute a 1 over dx squared there, what's going to end up happening is I'm going to be dividing each thing in here by dx, and that's still in the parentheses, right? So I multiplied everything through by a 1 over dx squared. But remember, dx squared under a radical is really just a dx, so I divided everything by dx, so I'm going to offset that by multiplying by dx. And then my arc length formula will turn into the antiderivative from A to B of the square root of dy dx, which is simply the derivative of your function with respect to x, plus dx dx, which is 1 squared, is still 1 dx. That is the formula we're going to use for arc length. The square root of dy dx squared plus 1 dx, and then integrate that from A to B. Here's a much more nicely written formula. If your graph is rectangular or Cartesian, meaning your graph is either y equals a function of x or x equals a function of y, this is your arc length formula. Exactly what I just showed you. The square root of f prime of x squared plus 1, and f prime of x is the same thing as dy dx. or if it's a function in terms of y, it's the same thing. It's just g prime of y squared plus 1 dy. Those are pretty easy. However, arc length is very common in vectors or parametric functions. So if you have your x and y both written as functions of t, the formula is pretty much the same, and it refers back and it starts to look more like this formula right here, where you had dy squared plus dx squared, or change in y squared plus change in x squared. If y and x are both functions of t, then that's exactly what we'll use. We'll use the derivative of x squared plus the derivative of y squared. They're both functions of t, and then we have to remember that our limits of integration and everything else is in terms of t. If you have a polar curve and you need to know the length of it, well, just like we did with polar derivatives and tangent lines, we're simply going to convert the polar to parametric using these two conversion formulas. X equals r cosine theta, y equals r sine theta, and then once you do that, your polar curve becomes parametric in functions of theta, and we can use this formula for the length of a polar curve. So there's an explanation of the formula. Now we're just going to do a few examples because they're pretty easy. They're easy to set up, usually very difficult to integrate, and because they're very difficult to integrate, these typically on the AP exam are either calculator questions or they only want you to set it up and not actually find the antiderivative. So here's my function. I will know the length from 0 to 1. Well, my arc length formula needs the derivative, so I'm going to find the derivative. Derivative of arc tangent x is 1 over 1 plus x squared, but this is 2 arc tan, so 2 over 1 plus x squared. And that means my arc length is going to be the area from 0 to 1, or the antiderivative from 0 to 1 of 1 plus, and then that function squared. 2 over 1 plus x squared dx. And then once you have that set up, we simply throw it in the calculator. And when we punch in the calculator, which I did over here, let me screenshot it in here, you get the decimal 1.871. Whoop, there it is. So these are typically calculator problems. If it's not calculator, then we will just set it up and stop. Do remember you always round and you'd be accurate to the third decimal, so it would be 1.871, or this is a case where you could just stop writing after the third decimal and use the truncating option, which is acceptable on the AP exam as well. So there's one arc length formula. You got to find the derivative, then you just throw it in the calculator. How about this one? This is x being a function of y, but that doesn't really change it. I now need to find the derivative. This would be the derivative of x with respect to y. That's a little bit unique. That is the same thing as all this stuff to the 1/2, so I'll bring down the 1/2 times, leave the inside alone. Subtract 1, make it negative 1/2, times the derivative of the inside, which is negative 2y. And just for the sake of making this easy to write, I'm going to clean it up. Half of negative 2 is negative 1. That y is in the numerator, and then I'm going to move that radical to the denominator, so that'd be the square root of 36 minus y squared. And then we'll set up the arc length formula, the area from 0 to 3. Square root of 1 plus that thing squared. So negative y over root 36 minus y squared squared, and this is a dy. And then just like last problem, we will throw that in the calculator. And there's our answer. Interestingly enough, I made these problems up off the top of my head without much forethought. I did make sure that I didn't have any domain issues. However, the answer to this one appears to be pi. So y'all can investigate that and see if you can figure out why. I don't feel like spending my time doing that. 3.142 or 3.141. Again, you could round using standard rounding procedures or simply truncate and quit writing after the third decimal. All right, so one more, then we'll call it a day. Here we have a parametric function, and for parametric we need to find each derivative. So x prime is going to be 2t, and y prime is going to be 12t squared. And so when I throw this into the arc length formula, it would be, negative 1 to 0 squirt of my derivative of x, squared plus my derivative of y squared dt. So there's our setup, x prime squared plus y prime squared dt. And again, we'll just throw that in the calculator. And when you throw that in the calculator, you get an answer of 4.149. So there's your arc length, fairly straightforward. You need to remember that formula. This will be used in the context of vectors fairly frequently. But there is your arc length.